Pleasure of introducing for our first talk in this morning's session, Joshua Fernandes from UC Berkeley, who will be telling us about bioelectrical phase transitions, collective effects in ion channel ensembles. So with that, Joshua, please take it away.
Hello, good morning, everyone. I hope you all can hear me from remotely. And yeah, I'm sorry I'm not able to attend in person this year. And big thanks to the Krell Institute for accommodating my circumstances. And yeah, I'm really excited today to get into my talk on bioelectrical phase transitions, which we see in systems of many ion channels that I did as part of my thesis work. And so, okay, yeah, so electrical signals in biological cells propagate along neuronal cells. So here, this is like a depiction of a neuron, and there's some kind of signal that transiently propagates down the axon called an action potential, which consists of a perturbation to the electrical potential difference or membrane potential across the cell membrane. And it leads to some event at the end of the neuron. And so what we're interested in describing is the physics of how the signal propagates along the axon. And this occurs on scales of millimeters and milliseconds, corresponding to speeds on the order of meters per second. And the molecular components that are responsible for this are these ion channels and transporters, proteins that are embedded in the cell membrane that are able to selectively move ions across the membrane and change the membrane voltage difference across the membrane. But these are nanometer scale elements, and the way that we try to describe how they might operate on a cellular scale has historically been through circuit models, the first of which were developed by Hodgkin and Huxley, who won the Nobel Prize for their work on this. But what these circuit models miss out on is the actual microscopic physics of what's going on. So for instance, the transport of ions across the membrane, the electrostatic effects of how the electric fields adjust, and the fact that the membrane is not kind of spatially homogeneous. A lot of these assume that the membrane is kind of the same everywhere and ignores the fact that these channels are discretely localized. And so for a lot of my thesis work, the question I wanted to answer was how can ion channels collectively show some behavior that's different than, say, individual ion channels, since a lot of the assumptions in the field have been that we can kind of, if we understand how a single ion channel behaves, then we know how groups of many ion channels behave. And so the first works that have looked at how we could have interactions between ion channels focused on two main modes. One is kind of clustering of ion channels. So this is where they might be physically next to each other and interact in some direct contact mechanism, or there might be membrane proteins that change the membrane and then therefore can have some signal that propagates through the membrane to interact with each other. However, what we're interested in is this topic of voltage-gated channels. So these channels may close and open in response to the membrane voltage. And then the question that we had was, suppose one of these channels, say, opens, here depicted with some lightning bolt, and when it opens, there'll be some current through it, which will change the membrane voltage locally and at nearby channels. And could it be the case that once this happens, the other channels are now maybe promoted to open because of the changes in the membrane voltage? And so this is the big question that I wanted to kind of answer in a lot of my thesis work, and I'll talk about some of the progress we've made toward it today. And so to answer this, the first question we wanted to answer was, how does a single ion channel generate this signal that propagates in space and time along the membrane? Since we couldn't really find an answer to this question, and then once we've answered that, we could then use that answer to try to figure out how many ion channels could behave and whether that differs from the behavior of single channels. And so I'll get started on this first question of a single ion channel. And here we have a depiction of what that might look like. And then our question is, how does this drive reorganization of ions in the system? And so suppose this channel is moving the cation, the positive ion, across the membrane. Would we expect it to just kind of spread out by diffusion, and that would be the characteristic reorganization process, or will it be something else? And we know that because ions are charged, they'll create some electric fields, which will presumably change this behavior. And so we developed a continuum approach to describe this system and understand the evolution of the membrane voltage, because that is the fundamental quantity of interest that is the signal that we're interested in understanding. So that's again, the electric potential difference across the membrane. And so I won't go into the details here about what this continuum description is. If anyone is interested, feel free to reach out to me afterwards or in the questions. But I want to bring up that there's a lot of kind of length and timescales that enter in this problem. So the opening of the channel is on the order of a few angstroms, sub-nanometer that is. Then there's this Debye length, which is the length scale on which ions will organize around the membrane surface, which is around nanometer scale. The membrane itself is nanometer scale. But the systems that we're kind of interested in that I mentioned before, like the cellular scale, can be millimeter or even larger. And then in time, the kind of fundamental time scale that ions are reorganizing by the surface is very short, again, nanosecond kind of time scale. But then the time scales on which these channels open and close can be up to milliseconds. So in both space and time, we need to span around 6 orders of magnitude. And this posed a big challenge for us to try to resolve. How do we resolve all the not molecular in our continuum approach, but how do we resolve all the nanoscale features around the channel while also retaining the information about how this signal is propagating over much larger timescales? And so we developed a finite element method mesh to numerically solve these equations that was variably sized. So here, this is depicting kind of what our mesh looked like, structured around the channel on the nanometer scale. And so it's very dense around this channel, where here the gold is where the membrane is and the blue is where the bulk electrolyte solution is. And here, as we zoom out, we see that this mesh that we made is getting coarser and coarser so that we can get to larger and larger length scales without having to have that same resolution that we need near the channel. And so this itself poses a number of computational challenges, which we won't get into, but fortunately, partially through the CSGF, we had access to resources that we could help numerically solve these. And so now I'll get into kind of what we saw from that, these simulations, and also subsequent analysis we did to understand the solution physically. And so once the current passes through the membrane, through this channel, it separates charge, where we have some net positive charge on one side and net negative on the other. And then this will instantaneously create some kind of electric fields, which will then drive further reorganization of ions. And initially, this looks like a dipole, an electrical dipole, where we have a small positive charge and small negative charge that are separated by a short distance. But what's interesting is then once the current continues to pass through, essentially these electric fields evolve such that there's this region depicted in yellow that looks like a monopolar electric field. You can see the field lines almost look like they're pointing radially outward, and we no longer have this dipolar-like structure. And this expands as time goes on and on. And essentially at long times, what we see is there's this, when we think about this signal that's propagating in terms of the membrane voltage difference across the membrane, it ends up being proportional to the current that's passing through the channel divided by the distance away from the channel we are. So here, this R is around the distance as we move along the membrane. And this ends up being pretty small for an individual channel. It's not surprising. It's like a nanometer scale object. It can only perturb the membrane voltage by around like 1 to 5% of its base value. But what's significant is that it has this behavior that's 1 over distance. Like, so if you imagine having many channels, you might be able to see that these 1 over distance interactions could add up to something significant and arbitrarily large. And in that sense, we say the signal is long ranged rather than something that's, say, exponentially decaying. And then the next component we added was confinement, because in many practical settings, the way we can manipulate or test these channels is by imposing some kind of external voltage onto them, here denoted by this EXT. And so when we introduce electrodes, we were curious, how does the presence of these electrodes affect the behavior of the channel? And then that will be relevant for how we can tune and test these channels. So once we have this was the original kind of electric fields we saw, this dipolar field generated by a single channel in some infinite medium, the unbounded case where there's no electrodes. And then once we introduce electrodes, essentially this red region shows the area where the curves are unchanged, but beyond that, the electric fields are changed significantly. And what I want you to take away from this is essentially within this distance of L, which is the electrode separation distance, we don't see really much change along the membrane, but further away we do. And so what we show is like essentially this means the signal is cut off at some length scale. So we don't see this signal that I just mentioned of the membrane voltage propagate beyond this distance, L away from the channel. And so with all of that, we kind of have this model now of how a single ion channel can generate this propagating electrical signal as seen through the membrane voltage. And we call this a kinematic model in that it's like we impose this current and we see what happens. And now what we want to look at is when we have many ion channels, how might these behave dynamically as they open and close and as the environment changes. And so to get into that, I'll talk about how these voltage-gated potassium channels, as that's the model system we looked at here, operate. And so essentially, they can go between a closed state where the ions cannot pass through the passage to an open state where ions can, based on changes to the membrane voltage, which is why we kind of started thinking about this interaction in the first place. And they do so because of this voltage sensing domain that changes its conformation as you change the membrane voltage. But firstly, this isn't a deterministic process. So here in this experiment, they step from a very negative voltage to a very positive voltage, and the channels begin to open. And this shows the current where the base current is 0, and then there's some current in the open state. And these are just 3 different channels. And what we see is that it kind of bounces back and forth between an open and a closed state, seemingly at random. And then secondly, the value of the current depends on the driving force, which is the membrane voltage. So in this experiment, if we went to a positive voltage, we'd see a positive current when it's open. If there is no voltage difference, there's no driving force. So we don't see any current, even whether it's open or closed, and we can't tell what the channel state is. And in the opposite case, we see a negative current when it opens. And so to understand why we might see cooperativity, this is a characteristic curve on the right of how the channel opens as a function of its local membrane voltage. So suppose we impose initially some external voltage at some threshold where only a small fraction of the channels are expected to open, but at least some are expected. Then what we might expect is like, okay, one channel might open here, but from the work that we did on the single channel, we expect this to perturb the local environment just a little bit, only by a few millivolts. And then when that happens, we move to a state where channels become more likely to open. And so that might, because it's going to affect its neighbors, it might lead to those channels opening, which might create a bigger effect and eventually lead to like many channels opening such that we move to a regime where the majority of channels want to be open, despite the fact that the condition we're imposing is where they'll mainly want to be closed. And then our question is, okay, this is a nice hypothetical effect, but how significant is it in actuality, depending on the system we're looking at? And so to answer this, we had to make a model for the dynamics of the channels, considering all of these features. And again, like before, I won't get into the actual like mathematical details, but I'll talk about the kind of physical motivation for how this can work. So here we separate our channels by some grid spacing of small l. And for a given channel, so here this one is kind of the reference one I'm thinking about, the voltage difference that it'll experience will depend on what we impose externally, plus whatever effect of current through its own channel, which will affect its own environment, and then the effect of all the other channels that are within this distance of capital L, a big L from each other. And then the current through the channel will depend on whether it's open or not. If it's closed, there won't be any current, and also the driving force, which is the membrane voltage at that channel. And then whether the channel is open or not will depend on its own voltage from those probability curve I just showed, as well as some randomness because of those fluctuations we saw. And so with that, we developed this Langevin equations to describe this and perform these stochastic simulations to understand. And we implemented these as a plugin in the package OpenMM. And before we actually simulated many channels, we calibrated our parameters to measurements on single channels. So we fitted all of our parameters before we even looked at interactions, and we're able to like recover the behavior of both the open probability on the left and the current through open channels. And now we could get to like thinking about many channels. So in this gray dashed line, we see what the behavior of a single channel looks like for this particular channel as a function of the externally imposed voltage. And then what happens is as we introduce many channels that are packed closely together, this curve actually changes a lot where the channels open at a much lower threshold. And so to see what this looks like, here is right around this threshold value, and blue is representing closed channels, gold open. And we see that channels kind of cluster together. Once they open, they'll open with their neighbors because of this kind of perturbations they cause. And what we also saw is as we lower the temperature, this curve becomes sharper and sharper. And so we wondered what will happen as we go to even lower temperatures. And what we saw was that there appears to be this discontinuity in the curve. So it jumps at some value to a larger open value, which is indicative of a phase transition in the sense of some discontinuous change in an order parameter, where here the order parameter is the fraction of channels that are open. And so here we look just above this threshold where we start from all the channels being closed. And what we see is they initially seem to just be mainly closed. And then suddenly we see this pocket where channels start to open. And because they're opening in a group, they start to cause their neighbors to open. And slowly this expands outward until almost all the channels end up in this open state, which looks just like the phenomenon of nucleation and growth, which is the way that many systems will undergo some phase transition. And then we're able to essentially do this at many conditions of temperature and the external voltage to create some kind of phase transition where we have states that are mostly open and mostly closed and some first order phase transition line that separates them, ending in a critical point. And then we're able to also apply a mean field theory to our equations to try to predict this analytically. And we say that we find this critical temperature scales with the kind of separation of these electrodes, as well as the density of the channels, 1 over the small L squared. And we recover behavior that looks qualitatively very similar. And what we predict is like, if we control the separation of the electrode, we should be able to tune this critical point and see this in real systems. And so with that, we're able to show like there's this non-specific interaction that can exist between voltage-gated channels, leading to coordinated activity, phase transitions. And in the future, we kind of want to explore changing the geometry. So this was all for a flat membrane, but the structures I showed you at the beginning were, say, cylindrical, and also what implications this has for real kind of electrical signaling. Here, this is all imposed externally. And I'd just like to acknowledge the people I worked with, everyone at Krell and CSGF, my practicum advisors, and all my other collaborators and funding sources as well. And thank you for your time, and I open up for any questions.